Yeah, I should just clarify a bit and hopefully say a little beforehand, because this is going to be, as I understand it, a very different kind of talk than is usually done in this series. And there's a little bit I will say, I'll try to remember at the end, about the connection of this to cosmology and the Big Bang, because there is one. But really, one way to think about this is that in order to make progress in physics, including cosmology, we have to find a way to put together quantum theory and the theory of relativity. And that has turned out to be just a very difficult thing to do in any kind of rigorous way. And I'm going to be making some suggestions about why that is and maybe a way forward. And I should also mention, this work actually is not in the volume that was mentioned. It's the second volume, which does not yet exist. It's not out, I mean, because I haven't finished writing it, of New Foundations of Physical Geometry, that this work will be the end of. So let me just share my slides. Okay. And I should also say, although this may be on a topic that most people here are not that used to thinking about, because this is a brand new idea, as far as I know, and developed essentially from zero, everybody should be able to follow what I'm doing. There's no technical background or whatever that you would really need. I'll try to explain the main issues at the beginning, but then there'll be a little bit of geometry that everybody should be able to follow. Okay, so why is there a problem putting together quantum theory, which is more or less the theory of matter that we have, and relativity, which is our best theory of space-time structure? Why is there such a difficulty joining them together in some way so that there's a single theory that covers both, which of course there must be, because nature has both. One of the issues is non-locality, that quantum theory displays a kind of breakdown of classical locality in a way that was demonstrated by John Bell. I think that Bell's discovery here is, in some sense, the most important discovery in the history of physics. He proved, for those of you who are not that familiar, Bell proved a set of inequalities, just purely mathematical inequalities, that if you do experiments in labs that are very far apart, or technically at space-like separation, so light from one lab couldn't get to the other lab in time to have any effect on its experiment. What Bell showed is that if the world is local in a certain sense, if causation and so on can't itself go faster than light, then there are certain mathematical constraints on the kinds of correlations you could see between the outcomes of experiments done in these labs. And so he proves this theorem, and then it's just a matter of going into the lab. Well, first you notice that quantum theory seems to predict violations of this inequality, and then you go into the lab and check, and indeed there are violations of this inequality. So there is some kind of non-locality in nature, and that means that in some sense there are connections between events that have to be superluminal. And the question is how to implement that cleanly in the physics, right? How to actually write down a physics in an explicit way that will have this consequence. Now, I'm going to talk about how this is done in a particular understanding of quantum theory, not because I want to convince you this is the right way to think about quantum theory, but I'm just making a conceptual point. So I want to talk about what's called sometimes called Bohmian mechanics, or the pilot wave theory, the de Broglie-Bohm theory, which is a way of understanding quantum mechanics in the sort of way that John Bell insisted we need, which is where it's all in some equations, right? The physics is reduced to some clear, explicit, precise equations that you can solve and analyze, and not some hand-wavy, vague talk that you don't quite know what to make of. For example, if someone says, well, things go a certain way in the physical world until there's a measurement, and then they go a very different way, and then you wonder, well, what constitutes making a measurement? I mean, what is the physical content of that? So this is the kind of thing Bell didn't like. And this pilot wave theory is the kind of thing he did like, just because it's an explicit theory. So let me explain that theory for those of you who don't know it. The ontology of the theory, that is what the theory actually postulates to exist physically, consists of two parts. There's a quantum state, which is what you would be used to if you've studied any quantum mechanics, so a thing that's sometimes called the wave function of a system, which is the main thing quantum mechanics uses to represent physical systems. But in this particular theory, there's something in addition to the quantum state, which is a bit unusual, which is that it postulates there actually are particles. That when we talk about particles like electrons or the Higgs particle or whatever, we're talking about that because there really are particles. There are point particles that are moving around and that follow continuous trajectories. So in this theory, there are such particles, and they do in fact move in a certain way. How do they move? Well, once I tell you what there is in the world, then I need to give a dynamics. That is, I need to give some equations that specify how those things behave. And because we have two pieces of this theory, the quantum state and the particles, I need two pieces of dynamics. Now, for the wave function, for the quantum state, the dynamics is the usual one that's used in quantum theory, which is given by the Schrödinger equation. This equation always obtains in this theory. So there's no such thing that you might have heard of, the collapse of the wave function. That doesn't happen in this theory. So it's always the wave function, the change in the wave function is governed by this equation. Again, without going into much detail, you notice on the left, you have this psi of x and t, that's the wave function. And this equation is telling you how it changes in time because you've got deep psi dt, and that's equal to this Hamiltonian operator h hat operating on psi. So you can fill in particular h hats and you get a dynamics that tells you how the wave function changes through time. It's a deterministic equation. It's a linear equation. It has various mathematical features that are well understood. But in this theory, in addition to the wave function, in addition to the quantum state, we have these particles. And the point of the theory is to say that everyday things like tables and chairs and stars and planets are made up of these particles. And so you want to know, well, how do the particles move? And so I need a dynamics for that. And that's given by a second equation, which is called the guidance equation. And there it is. Again, you don't have to worry too much about exactly what's going on, but you'll just notice that again, on the left, dq k dt is how the kth particle's position changes in time. So it's just telling you how the particle moves. And on the right, which specifies how it moves, is an equation that just involves psi. It involves the wave function in a fairly simple, it's really quite a simple equation. And this is why it's called the pilot wave theory. Basically, the point of having the wave function, the point of having the quantum state is that it guides the particles. It tells them where to go. And it does so in a way that's specified by this equation. Good. So to understand quantum theory in terms of this picture, you can always go into any actual experimental situation because you have these two explicit equations and say, all right, what's going on, right? What actually happened according to the theory, or what could have happened according to the theory? And we want to particularly look at the moment at spin experiments, which are probably fairly familiar if you've studied any quantum theory. You can, quantum particles, electrons and neutrons and so on, protons, have a feature we call the spin. And the spin is like an intrinsic magnetic moment. It's as if they're little magnets with north and south poles. And when you take an object like that and put it through an inhomogeneous magnetic field, a magnetic field that changes its strength as you move around in space, that can deflect the particle. And so experiments that look at these effects of spin, obviously are called spin experiments. They tend to, at least originally, were done with things called Stern-Gerlach magnets. I'll show you a picture of that in a second. And these magnets can be oriented in whatever direction you like to make the magnetic field vary in that direction. So we can orient the magnets in the in a direction we can call the X direction, and then prepare a beam so that all the particles, when they're fed in, are deflected in a particular direction when fed into that beam. Let's say we'll call it the up direction. So I feed this entire stream in of particles and they all get deflected up. And then I can turn the magnets 90 degrees into the Z direction and apply them to that same prepared beam. And then what quantum theory predicts and what actually happens is now the beam splits. Half the particles go one way and half the particles go the other way. In other words, if I can predict with certainty what will happen if I check for spin in the X direction, then I become maximally uncertain what will happen if I check for spin in the Z direction. That's an instance of what's commonly called the uncertainty relations. The better I can predict one thing, the worse I can predict something else. Now, what we have here is a deterministic theory. So the exact physical situation at the beginning of an experiment, together with the laws, determine how the experiment will come out. So we can go and ask, well, what if I do this experiment where half the particles are deflected up and half are deflected down? What makes the difference, right? What is different about an up deflected one from a down deflected one? And in this theory, there must be an answer. Now, the answer can't be in the quantum state because the quantum state is the same in all these cases. So the only other place you could find a difference is in the initial positions of the particles. And so the outcome of the experiment must depend on those initial conditions. And in fact, they do according to theory and in an extremely simple way. So just so you can understand this, and it's about the easiest thing you can imagine. So we have here a Stern-Gerlach magnet. You'll notice it's got a pointy part on the top and a non-pointy part on the bottom. You could say that the top part would be the north pole of a magnet and the bottom the south pole. And because of the different geometry, the magnetic field is now not uniform. And you'll notice that the rule is very simple. All of these indicated flow lines tell you what a particle would do if it started at one of these various different positions on the left. And if the particle starts above the midline, above the dotted line, it'll be deflected upward a certain amount. And if it starts out below that midline, it'll be deflected downward a certain amount, and nothing goes straight through. So you get these two clumps of the particles that end up here and the particles that end up here. And that's just a matter of where they started out. So you couldn't ask for a more simple and straightforward explanation of the observed statistics than that. And there's nothing particularly mysterious or puzzling about that. According to the way this theory is set out, when I prepare a beam, I can prepare the quantum state, but I can't prepare the precise positions. There'll always be a kind of statistical spread in the initial conditions. And so there'll be, some of them will be above and some of them will be below.